Welcome everyone, my name is Felix Faure. I work at CIRAD developing the Biofung Tool soil health measurement tools. Biofung Tool is a set of functional indicators for measuring the impact of agricultural practices on soil health. It was developed by Alexis Toumazeau of CIRAD and Ala Broman of IRD. To begin, I'd like to briefly go over the definition of soil health. It is the capacity of soil to function as a living system within an ecosystem according to its limits to support animal and plant productivity and maintain and improve the quality of air, water, and thus the health of plant and animals. We can see here that the central parameter of soil health is the soil's capacity to function. A small graph here to illustrate my point and, above all, to help you to difference between what is often confused in the literature and what I would like to clarify here. You see two soils, soil A and soil B. You can see that they can have different level of quality here. Soil A has a high quality, for example, a deep, silty clay soil that is very suitable for growing crops. We would say that this soil has a high potential level of performance compared with soil B, which has a lower potential level of performance. For example, a thin sandy soil. If I look inside this soil and measure their health, we can see very clearly on the graph that soil A could be less healthy than soil B. In other words, the actual level of performance and functioning of this soil system is lower for soil B and therefore less healthy. How is soil health conventionally measured? Firstly, and in the standard way, soil health is expressed as a sum of properties that is conventionally optimized. By this, I mean that we measured physical properties and chemical properties and biological properties. The sum of these properties ultimately provide the quality of the soil and traditionally maximize this property. But is this really the right metric? There are a number of ecosystems where, in the end, more is not really better. Here is an example of a paradox in the African savanna. The African savanna, more specifically the Lamto savanna in Ivory Coast, has sandy soils that are very low in carbon and extremely low in nitrogen. Because of this characteristic, this soil is considered to be poor and therefore of poor quality, poor health, and low productivity. And yet, the paradox is that it is one of the most productive ecosystems in the world, with 16 tons per hectare of dry matter. We explain this productivity when the quality of the soil is so poor. In fact, in order to understand, we need to measure fluxes rather than stock. What's important here is not quantity of nitrogen, but the flux of nitrogen mineralized from organic matter. The second difficulty concerns measurement, soil texture, pH, quantity of organic matter and depth. All these measurements are static properties, properties inherent to the soil system. These properties indicate that the soil is, but if we go back to the definition of soil health, we see that what interests us is not what the soil is, but what the soil does, how it works. What's more, most of these measurements are carried out after the soil has been sieved, dried, or crushed. They are sometimes burned during the measurement stage or digested by acid or other chemical products. Finally, these laboratory measurements do not respect the physical integrity of the soil. This reflects little or nothing of the reality of the soil functioning in the field. Finally, all these measures are the result of a reductionist view of soil. By this I mean that the soil system is considered to be the sum of its parts. The various properties measured are put together to explain the system as a whole. But this way of thinking does not take into account the interaction that may exist between the living organisms in the soil and the physical complex that surrounds them. This is largely what differentiates soil quality from soil health. Our aim is therefore to move from a stock measure, from static inherent property measurement, to fluxes measurement that reflects the activity of living soil organisms. This approach avoids the need to project function by measuring them directly. For example, I measure the quantity of earthworm I find in the soil. I can project that this earthworm will improve the structure of my soil. They should allow better infiltration of water, stability of soil aggregates. But to get a good idea of this function of maintaining soil structure, earthworms are not enough. So I want to measure the quantity of which also help to maintain the soil structure, particularly the aggregate, for example. But this would mean measuring all the living organisms in the soil and projecting all their action into the main function of the soil, in order to be able to project the function of their entirety. But even if I can do this work, even if I have enough specialized to carry out this measurement, to determine all the living beings in all these taxonomic groups, I will still be missing the interaction they have with each other and with the physico-chemical context that surrounds them, the soil system. This great complexity and the difficulties it creates have led us to wonder whether it would not be preferable to measure the function directly without measuring player. In short, do you really need to know that? Biofunctool measures three major soil functions: nutrient cycling, carbon conversion, and maintenance of soil structure. These three functions, defined by Kibbleweight in 2008, are carried out by living soil organisms. When selecting the Biofunctool component indicator, we were guided by three main criteria. Firstly, each of the indicators selected had to target at least one of the three functions mentioned: carbon transformation, nutrient cycling, or maintenance of soil structure. pH, or the quantity of organic matter of the soil, do not directly target one of these functions. They have therefore been removed. That is not to say that these measurements aren't important for understanding how the soil works, but they don't directly target the measurement of the function. The second criteria was that these indicators had to be at the edge of the field. This condition had to set in order to get as close as possible to the actual functioning of the soil. All laboratory measurements, such as microRES to measure basal soil respiration in the laboratory, or measurement of enzymatic activity, etc., were excluded from the selection, as they do not respect the reality of the function in the field. The third criteria was that we want this indicator to be low-tech and low-cost. There are two reasons for this. Firstly, a reasonable cost means that repetitions can be made. For a statistical point of view, this is very important for the reliability of the result. An indicator at 300 euros will only be produced from composite sample, 1 or 2 per plot maximum. At 1 euros, we can repeat measurement and be statistically sound. The second advantage of this criteria is that they make users more independent, since the indicators are easy to use. Transferability is also improved, meaning that we can offer them to a larger number of people, particularly those with limited resources to carry out a reliable measurement. 8 indicators were selected. Biofunctool measurements measured 3 main soil functions in the field. 3 indicators for maintaining soil structure, 3 indicators for carbon conversion, and 2 indicators for the nutrient cycle. All the results are analyzed together and transformed into a soil health index. I'm going to give you a quick overview of all the indicators in the Biofunctool basic set, starting with the nutrient cycle. 2 indicators: ion exchange membrane, which measures the nutrient available to plant and the soil, and mineral nitrogen in the form of nitrite and ammonia. We have recently introduced a method for measuring soil nitrite using an instrument called the nitrate check, which can be used to take measurement in the field. To do this, we need to sample the soil, extract it with water, perform a simple filtration, and then dip a reagent straight to measure the amount of nitrate in the solution. The formulation here will allow you to return to a quantity of milligram of nitrate per kilo of soil. If you have the possibility of carrying out our own laboratory analysis, you can do it. And in this case, you can use the standard method with a KCl extraction on the laboratory measurement that will be more accurate than the one I am proposing here. The second indicator of the nutrient cycle is ion exchange membrane. By incubating the membrane in the field for a few days, this method measures the ions present in the solution of soil. Ultimately, the indicator gives us a proxy for the ion available to plants. They mimic the action of the roots. After extraction with KCl, the ions retained on the exchange membrane are analyzed in laboratory. We have three indicators for the carbon cycle. CIRAD, which was developed by Alexis Toumazeau in 2017, provides a proxy for basal soil respiration based on CO2 emissions from microorganisms. POX, permanganate oxidizable carbon, which is measured of the soil's labile carbon pool, and lamina base, which measures the activity of soil mesofauna on small macrofauna. As I was saying, CIRAD measures the activity of soil microorganisms based on their respiration. To do this, we prepare a colored gel in the laboratory that changes color according to the amount of CO2 breathed in the soil by the soil organism. The cells are incubated in 24 hours and the absorbance measure at 570 nanometers. The difference between absorbance and T0 and at T24 hours give us the final results. This indicator is also very visual. Purple cuvette indicates very little respiration, whereas a yellow cuvette after 24 hours indicates intense soil respiration. But POX, which measures the pool of carbon oxidized by potassium permanganate, is a proxy for the pool of labile organic matter that is easily accessible or usable by heterotrophic microorganisms. How does it work? First, a potassium permanganate solution needs to be prepared in the laboratory. Then, in the field, oxidation is carried out by bringing the permanganate solution into contact with the soil. Finally, the absorbance is measured at 550 nanometers. The discoloration of a permanganate potassium is proportional to the amount of organic matter that has been oxidized. Latest indicators for carbon transformation is lamina base. Lamina is a small strip of plastic with 16 holes that have been filled with a mixture of cellulose, carbon substrate, typically wet flour, and gum arabic to create a glue. This substrate is laid out to fill the hole in the lamina. 8 lamina were then left for a fortnight in the soil, in the field, each measurement point. This period varies depending on the climate and can be as short as a few days in a tropical climate. After incubation, a score is assigned to each hole according to the state of degradation of the substrate. 0 for no degradation, 1 for total degradation. The average score for the 16 holes divided by the incubation time in day is used to calculate a percentage of degradation per day, and therefore a rate of degradation to the activity of the soil's mesofauna and small macro. Finally, the maintenance of the structure is measured using 3 indicators. The beer can, which measures water infiltration rate, stability of aggregates at 2 depths, and the VESS, an indicator of the visual structure of the soil. The beer can is a very simple measurement. A ring is inserted into the ground a few centimeters depth, and 10 bottles of water are poured one after the other. The infiltration timing of each bottle of water is measured. By plotting this transformation on a curve, a straight line can be drawn. The slope of the straight line corresponds to the rate of infiltration. The stability of aggregate in water is measured at 2 depths by sampling between 0 and 2 centimeters and between 2 and 10 centimeter depths in the soil. Stability is given by the resistance of the aggregate to disintegration in water and to dispersion during a back and forth cycle in water. We carried out 6 repetitions on each point to ensure greater statistical robustness. and the average of the 6 repetitions gives us the score for the measurement point for the indicators. To finish, the VSS, a visual assessment of soil structure. A monolith of soil of 25 cm deep is extracted of the soil. A score is awarded for each of the horizons identified based on the various criteria that broadly correspond to the shape and size of the aggregates and the degree of soil compaction. The weighted average of the score awarded to each of the horizons divided by the total depth of the block gives us the final score. Taken together, these 9 indicators give us a large and complex dataset to analyze. Several methods are possible. Firstly, an univariate analyze indicators by indicators. This is the most complete method, but also the most complex, because it requires links to be made between the different indicators and a good knowledge of the statistics and our system. The second solution is to carry out a multivariate analysis, a principal component analysis, which gives us a more global and synthetic view of our dataset. This is the preferred way to start our analysis, before potentially moving on the univariate analysis, indicator by indicator. This multivariate analysis is often very informative, but remains complex to interpret for a non-scientific and trained audience. This is why we have developed a soil health index based on an existing method developed by Obrio et al. In 2016. This index summarized all the results of the 9 indicators into a score between 0 and 1, with 0 indicates soil in poor health and 1 indicating soil in a very good health. This index is comparative. I will come back to this later, and it can only be used with certain restrictions. However, it remains a very powerful tool to discussion with the public that is less familiar with statistics, particularly farmers and agricultural advisors. In addition to showing you a few examples of results from biofunctional measurement, I'd like to highlight the condition under which this tool is applied. Here you see a graph of the soil health index between 0 and 1. Two situations are compared: Croix on the left, with 10 years of direct seeding and permanent soil cover, and Cantat on the right, the same as for Croix, but with a transition made 2 years ago, after a conventional cropping system. The color results are shown here, with the result for the carbon transformation function in brown, the result for the nutrient cycle in green, and the maintenance of the soil structure in blue. From an overall point of view, the soil health index is significantly lower for Cantat, which made its transition 2 years ago, than for Croix, which has been in operation for 10 years. A closer look at the functions shows that only the nutrient cycle function is significantly lower for Cantat than for Croix. In a second example, with the same graph, this time between Ville, 3 years of reduced tillage with a faba bean cover in winter, compared to Jache, with conventional cultivation on bar soil between rotation. Here, the differences are more marked, and all the functions are affected by reduction. I would like to highlight a limitation of this result obtained by the biofunctional soil health index. The assumption made when constructing this soil health index means that practices or cropping systems in the same soil and climate context have to be compared. Studies have been carried out all over the world in a variety of soil and climate conditions to ensure that the results can be applied across the board. Here are 2 examples, one in Cambodia and the other in New Caledonia, on very different soil and climates. Each of these studies compare a conventional farming system with a soil conservation farming system. It can be seen that the soil health index increases in both cases from conventional to conservation farming. You have to be careful, because the soil health index is in Cambodia and New Caledonia are not comparable. Just because the soil health index is higher in New Caledonia than in Cambodia does not mean that the soil is healthier in New Caledonia than in composites. The change in soil and climate context and the mathematical construction of soil health index do not allow us to do this. Only a relative comparison is possible. Biofunc tool can also be used to monitor plots over time. Here you can see a graph showing the soil health index as a function of time. These measurements were taken on a rubber plantation in Ivory Coast. The T0 measurement corresponds to the control. A few months after this measurement, the trees were completely filled and replanted. Subsequently, a new soil health index measurement was taken every 6 months. 4 treatments were compared and gradient of return of filling residue. We can see here that we can monitor change in the soil health index over time and thus measure the impact of this practice on functions. Large quantity of filling residues improve the resilience of the ecosystem, compared with treatment in which little filling residues is added. To conclude, I'd like to pick up on 3 key points from this presentation. Firstly, Biofunc tool is a functional approach to measuring soil health. Secondly, all the indicators selected by the Biofunc tool method aim to measure 3 functions: carbon conservation, nutrient cycling, and soil structure maintenance. Finally, Biofunc tool can be used in the same soil and climate context to compare practice or monitor the same plot over time. Thanks for the listening.